So, my name is Terrence Barkin. I'm the Executive Director of the Advanced Carbons Council. Many of you will have known us in a prior life as the Graphene Council. Today's topic is squarely focused on graphene, and I'm joined today by my colleague, Dr. Chirag Ratwani, a graphene material PhD who has studied at Bournemouth University and also the University of Manchester. And he will be presenting on the first topic, first principles. Basically, why does graphene behave the way it does? It's a very interesting and fundamental question, and I'm looking forward to that part of the presentation. In the second part of the presentation, we're going to be talking about pricing dynamics. Graphene is a relatively new material, does not have a set market price per se, and we want to discuss what are some of the dynamics that affect pricing from the perspective of a producer or a supplier, but equally important from the customer's perspective. To begin with, I just want to make some statements because we are talking about pricing and things that might be considered competitively sensitive. I want to make sure to understand that these opinions are our own. They are not to be depended upon to make investment decisions. We are not setting or recommending prices for anyone in this business. We are simply giving our observations on real-world data from the marketplace and trying to illustrate principles about why this material works the way it does, how it can be applied in different settings and applications, and what kind of questions both producers and consumers must ask themselves when it comes down to commercial decisions about using this material. I also want to make clear that as an association, whenever members or anyone who is meeting under the auspices of the Advanced Carbons Council meet, that you must respect and comply with any antitrust regulations. Therefore, we do not discuss any material that is not publicly available. We do not engage in price setting and setting up quotas or setting up territories or quantities, etc. What we are discussing and what we're very happy to discuss with you today are issues that are of importance across the industry and that are generic examples of how pricing works and also about the technical details of these materials. We just want to make sure everybody is clear about compliance with antitrust. For those of you who are not familiar with the Advanced Carbons Council, as an organization, we have been around now since 2013, and today we reach more than 40,000 materials professionals worldwide that are working with advanced carbons. We are a trade association, which means simply our members are companies and organizations that are engaged in this area that we support and serve. And so with that, before we go to the first part of our presentation today, I'd like to introduce Dr. Chirag Ratwani. He works for us based out of Manchester, UK. And with that, Chirag, I'm going to hand over to you and I'll drive the slides and you let me know when you want to progress.
Yeah, thank you so much, Terence. Hello everyone. For this presentation, before we go any further, let's reset to fundamentals. And when we say graphene, we are not talking about a marketing term. According to the ISO standard, graphene is very precisely defined as a one atom thick layer of carbon atoms, where each carbon atom is bonded to three neighbors in a two-dimensional honeycomb structure. For practical purposes, the same standard defines graphene-related 2D materials as carbon-based two-dimensional material consisting of 1 to 10 layers, which is more commonly used in commerce. Now, this is a slide that everyone loves. This is why graphene came under the spotlight. The numbers here for different properties are remarkable. You'll see that thermal conductivity is among the highest ever measured, the strength far beyond steel on a weight basis, electron mobility that outperforms most of the materials, and all of it in a material that's just one atom thick. It's incredibly light, extremely stiff, highly conductive, yet flexible and almost transparent. But here's the key point. These are not isolated strengths. They all come from the same thing, the atomic structure. And in the next few slides, we'll see how that structure translates into mechanical strength, thermal transport, and electrical behavior. because once you understand the mechanism, you can start to engineer with it. So how can something one atom thick be so strong? So the answer is that each carbon atom bonds to three neighbors in a perfect hexagonal lattice, like flawless atomic scale chicken wire. These carbon-carbon sigma bonds are among the strongest in chemistry. Unlike metals, there are no weak slip planes and no easy deformation paths in a perfect sheet. The load is distributed evenly across the entire 2D network. So when you pull graphene, you're stretching the carbon-carbon bonds directly. Now, failure only happens when those bonds break. So that's why the tensile strength reaches around 130 gigapascal, which is roughly 200 times stronger than structural steel on a weight basis. So now let's talk about heat. In solids, when heat moves, it moves through vibrations. Like in atomic motion, these vibrations or phonons travel through the lattice and transport heat. Graphene's carbon-carbon bonds are extremely stiff, so when they vibrate at high frequencies and transfer energy, it is very efficient. And because graphene is a nearly perfect two-dimensional crystal, there are very few defects or grain boundaries to scatter those vibrations. So heat can travel long distances with minimal disruption. The strong bonds, efficient vibrational transfer, or minimal scattering, uh, this results in thermal conductivity that outperforms copper at a fraction of the weight. So now comes another important property, which is electrical conductivity. And this is where graphene becomes a bit fascinating. Most materials need a slight push before the electrons can start moving. And this is usually an energy barrier, which we call as band gap. That electrons must overcome to conduct electricity. Now, graphene in that sense is very different. It has what we call a zero band gap. That means there's essentially no energy barrier preventing electrons from moving. Electrons don't need to be excited to cross the gap, they are already free to respond. But that's only part of the story, because as you remember earlier, we mentioned that each carbon atom forms three strong bonds, leaving one electron in a p orbital. Now, these p electrons don't belong to one specific atom. They are delocalized and they're spread across the entire sheet. So instead of isolated charge carriers hopping from atom to atom, you have a continuous electron pathway across a perfectly ordered two-dimensional lattice. And because the lattice is so uniform, electrons experience very little scattering. So now, once you understand the structure and the mechanisms, the application landscape makes sense. So graphene and the advanced carbons are not limited to one sector. They are platform materials, so they can enhance composites, improve batteries, strengthen concrete, enable flexible electronics, improve corrosion resistance, etc. And in many cases, they don't replace materials, they rather upgrade them. And that's where the real impact lies, the incremental improvements across multiple industries that collectively support efficiency, durability, and ultimately a lower carbon economy. So this is the slide where we move from physics to the physics to reality. So in industry, you don't simply buy graphene. There's a whole range of materials that fall into the category of graphene and related 2D materials. Here are some examples like fuel air graphene, graphene oxide, shell graphene, or turbostratic graphene. As you can see from the image and Raman spectra, that they're physically and chemically distinct from each other. The last one on the far right is amorphous carbon. Now, this may look visually similar, this may look similar visually, but electronically, chemically, and mechanically, it is a completely different material. Now, this brings us to a critical point. So in industry, you're not buying a name, you're buying a specification. So if we agree that not all graphene is the same, the next question is how do we define what we are buying? And this is where the ISO 9651 standard plays an important role. It's the graphene classification framework. So this was developed by the Graphene Council with the help of volunteers, and now it's converted into an official ISO standard. This moves the conversation from marketing language to measurable parameters. So this framework defines what characteristics matter the most for commercial use, how those characteristics should be tested, what measurement ranges can be expected, a consistent naming syntax, and even a structured technical data sheet format. Now, from the image on the right, when you look at the breadth of parameters, you see production method, layer number, lateral size, data potential, crystallinity, etc. Now, these are 19 distinct characteristics that together define performance. And because graphene performance is multidimensional, you cannot reduce it to a single number, not surface area, not purity, not even price per kilo. So this framework allows producers to report consistently, and it allows buyers to compare the materials transparently. And ultimately, this is what can enable industrial adoption at scale. So how do you use such standards in practice? So let's look at it from both sides. Now, if you are a graphene producer, this is about being spec ready. So when your material data follows a consistent structure, customers can drop it straight into their qualification metrics. It makes batch consistency visible, not disclaimed. And if two materials look similar on paper, then the differentiation has to be real and not just in branding. This also reduces back and forth across regions because everyone is working from the same format. Now, on the other hand, if you're a graphene consumer, the starting point shifts a bit. You begin with specifications and performance thresholds and not product names. You look at the reported ranges and test methods. The variability tells you a lot about process control maturity. And make sure you separate form from function, like graphene oxide, fuel layer graphene, defect-rich materials. These are not interchangeable, and the framework helps prevent that confusion. Ultimately, this standard changes how graphene is evaluated, purchased, and can be trusted. So, how do you actually choose the right graphene for you? I'd break this into three steps. First is understanding the TDS properly. Now, don't you should not just glance at the headline numbers. You should look at the full technical data sheet, check how the material is classified, and see what's reported. And just as importantly, what's not reported. And try to separate the real data from marketing language. Second is to be very clear about what matters for your application. Is it electrical conductivity, thermal management, mechanical reinforcement, or barrier performance? What's the most important property for your application? Because not all 18 classification parameters matter equally in every case. So selection has to be application driven. Otherwise, you may end up optimizing for the wrong property. And third is to test it in your actual system. So a lab data on a powder is one thing, but performance inside your polymer, your coating, concrete matrix, etc. That's what counts. Along with that, you should check for dispersion, compatibility, and basically how that material is going to be used in your application, not just the final result for that. Because at the end of the day, the right graphene is the one that performs in your formulation. So finally, let me leave you with this image. Two jars, both labeled graphene, same price per gram, but they're not the same material. We have reviewed more than 850 technical data sheets in the market, and fewer than 15% of them report all the essential parameters needed for proper qualification. And that's a problem because if you don't know the properties, performance becomes guesswork. So on paper, materials can look identical. In reality, they can behave completely differently. So this is exactly why structure, classification, and proper reporting matters before we even start talking about price. Because price per gram only makes sense when you understand what you're actually buying and if it works equally well in your application. And with that, I'll hand over to Terence, who will take us into the commercial and pricing side of the discussion. Thank you.
Excellent. Thank you, Chirag. Really appreciate that. And that's a perfect segue then into our next topic. So in this particular graph, we're going to approach it from a perspective that we have a particular application, and we've determined we want to improve the performance in that application, but we have a threshold that we cannot tolerate more than a 0.25, 25-cent US per kilogram additional cost into our particular product, whether that's a thermoset or a thermoplastic or a polymer coating or a battery matrix or whatever the application is, just purely from the calculation of a price tolerance for additional cost for an improved product. We've arbitrarily picked a 25 cents per kilo additional cost threshold. And what I wanted to illustrate with this particular graph is that we could have materials that cost as little as $50 a kilo, so graphene A or that light yellow line, or we could have a graphene that costs 50 times as much, or 30 times as much in this case, at $1,500 a kilo. And this full range of price is representative of the range of prices that you will find today in the market for graphene materials, depending on the type and grade and format of the material. But what this shows us is that the key factor which makes using graphene so much different than typically sourcing other materials is there is a really wide range of load factors. It's as if you asked for a quote for somebody to paint your house, and one painter said, I'm going to use a gallon of paint and cover your house, and another one says, I need 100 gallons of paint and I'm going to cover your house. That normally doesn't happen. But with graphene, you have very, very different load factors that could be a factor of 10 or more different from one another. And that load factor is what enables what is ostensibly a high price material to still meet your target price threshold. So that's what we try to illustrate with this particular graph to really highlight the role that the load factor has in affecting what price point is acceptable for a commercial application of the material. Now we're going to use three different very specific applications, and I'll walk through this briefly with you, and you can refer to it in the slides in more detail if you'd like to get into that. But in this example, we're assuming that we're putting graphene into the liner of a pressure vessel, a type 4 hydrogen pressure vessel, which is a thermoset carbon fiber composite outside, but a thermoplastic liner inside. And in this 62-liter hydrogen tank with about 55 kilos total mass, the liner is about 12 kilo of that. So on the grid that you see on the left, the PA11 material for the liner costs $15 a kilo. There's 12 kilos of it, so cost of goods is $180 US. And then on the second column under graphene A and graphene B, graphene A is $100 a kilogram, graphene B is $200 a kilogram. Graphene A is added at a 1% loading, graphene B is added at a 0.4% loading because it's a different material. It ends up being the exact same cost per kilogram added at $1 each because of the different load factor, or 6.7% of the total cost. So now when we drop down to the bottom half of this table, we assume that because of the improved performance of the graphene and that it would allow us to reduce 25% of the virgin material because we're getting a much better performance out of it. And this is based on data that we've actually recently tested. So the mass of the virgin material with the graphene in it now gets reduced to 9 kilograms. So the cost of goods drops to $135. The added cost of graphene in both cases is $9, even though one is priced 2.5 times as much as the other, but because of different load factors, you need less of the second. And the net result that we see is that there's actually a cost of goods savings by adding graphene, even though it's at $100 or $250 a kilo. the customer in this particular case is actually saving $36 per unit, or a 27% savings on cost of goods for this component. So that's one example where you can actually add this material, get a better performance, and reduce cost at the same time. In our second example, and we'll have three different price points to illustrate this, we're going to look at cement and concrete. This is a market that an awful lot of people are interested in because it's massive, and it also represents 8 to 9% of global CO2 emissions, and there's a tremendous interest to reduce that carbon footprint. So in this calculation, we've taken a cubic meter of concrete, which weighs approximately 2,400 kilograms, and then we're using ordinary Portland cement as the example. A typical formulation might be 15% of the mix is Portland cement. You can have higher or lower. This is just for illustration. 15% is quite illustrative. And then you have your fine aggregates and you have your coarse aggregates in a concrete mix. You see them there as a percent of the total at 15, 35, and 50%. And the price per kilo, all of these materials are incredibly inexpensive because they are mass produced and they're commodity price driven. So cement is about 15 cents per kilo, where the aggregates are at the 3 US cents per kilo. So on the fourth column over under cost, you have your cost of materials. So a cubic meter of concrete, the actual cost of materials, this isn't the retail value that it'd be from a ready mix company to sell, but the cost of ingredients calculates at $114 for 2.5 tons. So an extremely inexpensive, cost-sensitive material. Now, if we drop to the second half of this table and we look at the addition of graphene, we have the same cubic meter of concrete, but now we're going to add graphene at an extremely low load factor. So you've got 0.042 kilograms, or just 42 grams of graphene added to this mix. And with that graphene priced at $50 a kilo, we're adding $2.10 to the cost of goods. But because graphene enhances the strength quality and we're able to then reduce the cement component out of our concrete mix, we assume we can take 15% of the cement portion out of this concrete mix while retaining the same strength or better profile and also getting better cure times, which is typical. But let's just focus on the CO2 reduction. The cement, of course, is almost entirely responsible for the CO2 footprint for concrete. So now we're removing the cement portion from 350 kilograms to 295 kilograms. The aggregate, the fine aggregate, goes up to 900, and the coarse aggregate goes up to 1,205 kilos, so that we get our total original weight there. The net result is that we are going to reduce the actual cost of goods bill for this cubic meter of concrete by $4.50, which is a 4% savings in cost of goods. Plus, the big news is that we get at a $50 per kilo of the graphene, we save the 4%, but we're also reducing by almost 16% the carbon footprint. So now if you're a ready mix producer and you're able to apply this, you can go to the market with a low CO2 cement that actually costs less for you to produce, where you could either sell it at parity with the normal grade material, or you could, of course, ask for a premium. Now, if we use a higher price material, $100 a kilo, we see that at the same load factor, you still come in under cost compared to the baseline, and you still have the same CO2 reduction. And if you go to as high as $250 a kilo for the graphene component, at everything else being equal, you now come in at an additional cost of $3.90 per cubic meter. And the question would be, if you do have a low carbon concrete, if the ready mix company could add even just a 10% premium, you are still more profitable with this use of graphene, even if you're paying $250 a kilogram, given the load factors that we use. So there's an example in concrete and how this pencils out. Now, the third example is going to be in commercial vessels on the ocean, where you have ballast tanks. These ballast tanks have to be coated because obviously they come in contact with salt water and with other very corrosive elements. These tanks require inspection and spot maintenance over the life of a vessel. A minimum life of a vessel, a commercial vessel, is about 20 to 25 years. The International Maritime Organization requires paints for ballast tank coatings to be rated for a life of 15 years total. So not the total life of the vessel, but 15 years is what the minimum rating is. And if you have a typical Panamax, and that just means the largest vessel that could go through the Panama Canal prior to the enlargement of the canal, they may have 30,000 to 40,000 square meters of ballast tank surface to be painted. That's per vessel. The thickness of it comes down to 320 microns, and that's about 9.9 kilo or a kilo of coating material per square meter. And for this application, we're assuming an addition of 0.3% of graphene added to the polymer to improve the corrosion reduction. So in these tables, I apologize, they're a little bit small because there's a lot of data to put up. But on the left table, you have the untreated standard approach. So you have 10,000, we're assuming just 10,000 square meters. As I mentioned in the previous slide, it could be 30 or 40,000 per one vessel. I'm using 10,000 just to illustrate some numbers here. So we're assuming 10,000 square meters of ballast tank surface to be painted. You're using 9,000 kilograms of paint coating for that. Because it's a bulk product, it's as cheap as $5 a kilogram, so that your cost of goods is $45,000. But when you add all of the labor and the cost of actually applying this in a shipyard, it ends up being $75 per square meter to coat. So there's a $795,000 investment for a new vessel. Now, once that vessel is underway and working, from year 6, you start to have corrosion problems, and they do spot maintenance. And the assumption here, based on data from the industry, is that about 2% of the total area is going to need to be repainted and spot protected. So that equals about 200 square meters of area that needs to be painted every year from year 6 until year 15. So 10 years of maintenance at about $125 a square meter, because once that ship is launched and you start to do repairs in the ballast tanks, it gets more expensive per square meter. So that's $25,000 a year in maintenance for years 6 through 15, or $250,000 over that 10-year period. On the right table, we have 10,000 square meters, 9,000 kilograms of material. That's all the same. But in this case, we've added graphene at 0.3%. So that's 2.7 kilograms of graphene for that 10,000 square meters, or $945. And we're assuming a price of $350 a kilo. So not the cheapest graphene, to give you an illustration of what that can mean, even with a higher price material. So labor in shipyard is the same. That means the initial investment is another $945 compared to the baseline. Now, because this is a superior corrosion product, we don't have to repair as much area because it won't corrode as fast. So now it's only 1.5% of the area, or 150 square meters per year, that needs to be coated. And at $125, that's $18,750 a year for repairs. So over 10 years, we are saving, for a $1,000 invested added cost in the paint, we're adding $62,000 in savings, or a 60 times ROI for that $1,000. But this is only half of the story, because for any major infrastructure, whether it be ships or it be bridges or it be steel structures or petroleum plants or ballast tanks or whatever the asset is that needs to have corrosion protection, and there are just unlimited examples of this, It's a major capital expenditure to repair them and from corrosion. And so if you can delay making your major repair, so for a commercial vessel, after 15 years of life, the ship owner has to decide if they take the ship out of service or if they want to continue. There is a major refit to be done for the ballast tanks, and that's estimated in our example at $375,000 for the refit. If you could postpone that from year 16 to year 20, that's worth an additional $81,000 in deferred expenses at a 5% discount rate for net present value. And that, for anybody who's an asset owner of a large asset that needs this kind of work, will appreciate the value of delaying these major maintenance costs further down the road. So this is just a different example of how it can be calculated. Where does it make sense to add graphene? So that $1,000 additional cost of adding graphene in this application totals more than $140,000 in realized savings because of deferred maintenance and lower corrosion expense. So that's a pretty strong illustration, and we just wanted to use these examples to show that this material, regardless of what the cost may say, it really depends on the amount you need to solve your engineering problem, and that it's important for both the customer and for the producer to work through these examples to understand what the value is of using graphene in those applications. The Advanced Carbons Council is a global trade association. We are a neutral party. We do not make these materials. We do not sell them. We do not get commissions. We have no financial interest in any of the companies. We're here as a science, fact, business-based organization to help both the producers and the users of all advanced engineered carbons on how to use them and apply them in their business for competitive advantage or to solve major engineering challenges and problems. So we cover the full spectrum of these advanced materials. Graphene is an interesting example as a newer material that holds a lot of promise, but a lot of these other carbons also can be used in combination depending on what your particular engineering challenge is. The Advanced Carbons Council has a wide palette of services available. We regularly disseminate information. Things like this webinar is an example. We have networking opportunities at events and conferences, which are coming up this year, and you'll receive that if you're on our mailing list. Our main engagement method is to have members to engage with us on market reports and get access to privileged information as a member. And then we also work with companies for verification and due diligence, as well as material testing and characterization. We issue technical data sheets. We can help companies with safety data sheets. We can advise you if you're a customer. We can advise you if you are a producer. We even help with regulatory approvals for companies that need that assistance. So basically, if you have any question about an advanced carbon material, on how to use it, how to procure it, who's a trusted supply chain partner, you can come to us for independent, neutral advice on that. And with that, I want to say thank you to everybody who's attending, and we will now go into a Q&A session. But before we jump to that, my last point I want to raise with you is we are currently conducting a survey. We do this every few years. We don't do it every year. We do it every 3 or 4 years, and we conduct a comprehensive survey. Whether you are new to this material or you've been using it for decades, whether you're a researcher or you're a customer or you're a producer, we encourage you to put your opinion into the graphene survey. It only takes about 5 minutes to complete it, but it's incredibly important. So if you haven't already received an invitation to take the survey, you can also use this link or use the QR code to access it.
One of the questions that just came in but caught my eye was why not adding more percent of graphene in the applications makes them better? For example, 5% graphene for the cement. Is there a limit? So the exact concentration of how much graphene you can add and what is the most beneficial amount for you depends on your application. Uh, in most cases, graphene works a little counterintuitive to what we see with other materials. So adding more graphene always does not mean better results. For example, if you're using graphene in a composite And if you end up using more graphene than you need, then because of the layered structure of graphene, that can promote slippage of graphene planes over each other and thereby making the composite a little weaker. So that's why finding the right optimum quantity for your application is essential.
Excellent. Excellent. Um, there are a lot of different numbers or questions in here. So some of the questions relate to the numbers that we used, asking, are these real world numbers? How did we come to that? The reality is the whole genesis of this is because we were working with a particular client that was looking at this area, and they asked us two basic questions. We trust you when you say graphene does what it says it does, but why does it do that? And that generated the first presentation, and Chirag, I think, did a good job of explaining that for three of the most important properties. And the second question was, if I have a graphene that is, 3 to 5 layers and it's 98% carbon and it's a certain flake size, what is that worth, or what is the price for that? And the reality is that this is an incredibly fluid market in terms of pricing, and there is no reference price, there's no reference material. The pricing really is quite variable from producer to producer. There are more than 200 companies that we have cataloged and profiled, and we're about to publish the most recent edition of the Graphene Report. We're in the final stages of review, and then that will be published. And members of the Advanced Carbon Council will receive a copy of that report. And if anybody's interested, it's also available for purchase. But in the graphene report, we have more than 200 companies. Some of them produce very small amounts. Some of them produce quite significant amounts of this material. And that accounts for a difference in price. Some of the production methods are quite efficient, and some of the production methods are quite expensive. So there's a huge variation in price. And then when you look at the load factor, you literally could have a material that you load at 0.003% by weight or 0.1% by weight. And so there's a massive difference in the amount of material that's used for that same application. So I hate to give the answer, it all depends, but to be honest, with graphene, as Chirag reported, we've cataloged more than 800 different form factors of graphene that are commercially available. And depending on your application, uh, different materials will work. And it is not the case in almost any case where only one graphene will be the one that works. There's usually options. So you have to balance how effective is this particular kind of graphene that I'm looking at, which tells me how much of it do I need, and then you have the price factor. And that's, it's a little bit of work, but it's worth doing the work, because it might be that the more expensive material you have is actually more economically feasible. The very baseline analogy I like to give is, you can buy yourself a really cheap pair of shoes and you're going to buy a new pair every year, or you buy a fantastic pair of shoes and you'll have them for the rest of your life. Which one is more cost effective? So, buying the more effective product, even that it's more expensive, often can be the better economic decision. I hope that answers some of those questions. Chirag, do you have another one?
Yeah, there are a few questions about use of graphene and energy storage related to solid state batteries, solid state supercaps, but also alternative chemistries. So, with advanced carbons have always been used in batteries, mainly in the form of graphite. Nowadays, a lot of the other materials, including carbon nanotubes, graphene forms, etc., are finding their way into the into the battery chemistry. With graphene, when you add it to batteries, it can be added in different parts of the batteries, including cathode, anode, or even in some of the solid state electrolytes. The main benefit that graphene brings in is the increased electrical conductivity and also the robustness of that component. We right now we know that there are some solid state electrolytes that are in development. There is graphene that's already being used on the cathode and the anode side. Uh, for But it also helps us enable some alternative chemistries. Like there are companies that are developing lithium sulfur batteries with graphene as a host. There are also companies that are working on graphene-based lithium or silicon batteries. So silicon as the anode. So graphene, I think, is it also helps in the incremental improvement, but can also enable alternate chemistries.
Excellent. There are a couple questions related to what are the raw materials for graphene? What are some of the production methods? So I'll answer that in a general way. There are about a dozen raw materials. This could be anything from carbon-bearing gases like acetylene or methane or methane. Could be traditionally it was graphite. That was the original, was exfoliating graphite materials, but it can also be made from recycled plastic materials. It's also being made from biomass. So you have conversion of biomass into biochar and then biochar further processed into graphene or even carbon nanotubes. So on the raw material side, it's almost any carbon-bearing substance can theoretically be turned into graphene. The economics of that is the next question. And then on the production methods, there's also quite a number of opportunities on production method. It could be flash Joule heating, flash Joule heating, normal pyrolysis, mechanical exfoliation, electrochemical processing, pure chemical processes, which accounts for the wide variety in types and morphologies of graphene and a wide variety in the cost base of production because there's different raw material costs, there's different production costs, different energy inputs, and different economies of scale. So, as a customer, it's good to be aware of these things, but you don't need to be an expert to understand how to use it. I think what is really important from a customer perspective is first understand what is the most important attribute you're trying to improve, whether it's strength, lightweighting, energy density, or rapid charging, or electrical conductivity, or barrier protection, or there's even graphene in this shirt, which gives it tremendous abrasion resistance. So it depends on what you're trying to do, and then use somebody like us to help you navigate this, or get in touch with qualified, bona fide graphene producers to match the right kind of graphene to your application. Understanding what's behind it, I think, makes you a better educated consumer of the material so you can ask the right questions, but you don't need to be an expert to know how to use it. You need to be an expert to know what you're trying to achieve with your product. And the good news is, because there's so many form factors of graphene, there's likely to be at least a few of them that will work for you. Chirag?
Yeah, I do have a question about corrosion resistance. So, what base property of graphene allows for corrosion resistance? And for this one, so graphene works in different ways when it's incorporated in a coating. When you add graphene to a coating, firstly, it helps form a tortuous path. So that means a longer path for moisture, for oxygen to reach the metal surface. So that's why there's delayed, like corrosion happens after a really long time. Second is when you add graphene to the polymer for the coating, it helps enhance the polymer as well. So thereby improving the scratch resistance or the strength of the coating. So it makes it difficult to scratch, tear, etc. And the third one is because graphene is very light in weight and you're usually adding it in very little quantities. It does not increase the weight of the coating like other additives do. So that's you're not increasing the thickness or the weight of the coating, and you can also improve the corrosion resistance at the same time.
I think that's a really good point, Chirag. And I think we have to also not forget in the early days, many of the paint companies were really hesitant to even think of graphene because they said, why would I put an electrically conductive material in my paint? I'm going to have cathodic corrosion. And the reality is you're using such small amounts of it, you don't create, unless you intentionally want to, a electrical conductivity in the material, but you do get the barrier property. So that's often a question with coatings. Why would you put a conductive material into the paint? Um, there is a question about greenhouse gas credits, and we have seen that especially with biomass-derived carbons, that the carbon credits are a big driver of that. We have not seen that much for graphene, but if you think about the reduction capability of using graphene to reduce your carbon footprint, or using, for example, There's more than a few companies that are taking excess waste methane or methane gas and converting that to graphene. So you're diverting this gas and CO2 emission into a physical product that could earn credits. I think that is an aspect that deserves a lot of attention because it's another source of revenue. And with the proliferation of AI data centers, we see now the private market for carbon credits is getting quite buoyant. I think it was Microsoft that had announced they were going to invest at least 200 million in voluntary carbon credits to mitigate the footprint they're going to have from the data centers. So we're not reliant then on obligatory or mandatory carbon markets, but the voluntary market is one that I think everyone in this sector should at least be aware of.
Yeah, absolutely. I'm also seeing a good question about what about adding graphene to asphalt? And I think that's one of the very interesting application areas because adding graphene to a binder like bitumen for asphalt helps you with the rotting resistance and helps improve the life and the longevity of such asphalt materials. With Advanced Carbons Council, we have now tested, I think, more than how many samples is that, Terence? We have tested different kinds, I think.
Yeah, I don't know, we've
Yeah,
tested a
yeah,
dozen.
a lot of the graphene samples have been tested in bitumen and how they have improved the asphalt or the asphalt properties. And this testing has been done with our partners in the US, where the specifications used were exactly same that the Department of Transport uses for the highways and everything. So we have seen that graphene works. It helps make the asphalt last longer. It helps with reducing the embedded carbon and it's one of the emerging applications for graphene.
Absolutely. One of the questions, a good question is, how do you test the material for some of these characteristics? So first of all, the ISO 9651 standard, the graphene classification framework, lists the characteristics that we believe are important commercially, and that was based on the input of more than 100 volunteer experts worldwide. But in that standard, it lists which characteristics. It also lists which test method is recommended for each of those. And of course, the Advanced Carbon Council does a lot of material testing and characterization. We're one of the few organizations that can actually conduct all of those tests and create the complete technical data sheet using one facility compared to the way most testing is done, which is some of it's done at a university and then some of it would have to be done at a different facility. So you're splitting the lots, but we can do comprehensive testing, and we've done quite a lot of that. Not only the raw material, the graphene, but we've also done article testing. So somebody will have a material or they'll have a product, and they say the producer claims to have graphene in it. Is there graphene in this product? And we've done that kind of destructive testing as well, just in case anybody needs something like that.
Uh, yeah. Terence, I'm going to take the next two questions if that's okay.
Yeah,
Both are
sure.
very
Of course.
interesting. And yeah. So the first one is why industrial grade graphene price is very low, whereas the R&D grade graphene price is very high. The simple answer for this is the economies of scale, that if you buy graphene in a larger quantities, the prices can get more effective because now you're committing to a larger purchase and the manufacturer can make it a bit more efficiently. So that's one reason. The other reason is because on the R&D grade graphene, there are many different types with very minute nuances that can be obtained from the market. On the industrial grade, there's a little less variety of graphene that can be obtained. So depending on the type and the different properties, the price can be very variable. And depending on the quantity or how it's been tested, the price can change. Yeah. And the second question that I saw was finding the optimum quantity is one task, but the proper incorporation of graphene is usually a challenge. What are your thoughts on that? So, yes, absolutely. I think finding the right dispersion method, finding the right way to apply graphene in the application is actually equally important, if not more, than finding the optimum quantity, because you can add a little less or a little more graphene into the matrix. It wouldn't matter if it's not dispersed properly to have the best effect of graphene. Because it's a nanomaterial, it has to be distributed evenly. It has to be applied in a way that it becomes more effective. And because it's a two-dimensional material, so properties are also dependent on the direction. So in some cases, orientation of flakes or agglomeration would play a huge role in determining the effectiveness.
Absolutely. We have a couple of questions asking what is the size of the graphene market in general? Where, what is production capacity? Where do we see that going? This is all the kind of information that, of course, is in the graphene report that is coming out here and quite shortly. But in general, we're about 25,000 metric tons of production capacity. And I would say production capacity is not the constraint at the moment. It's the offtake partners and getting graphene into the commercial applications. Hopefully today, what we've tried to illustrate is the feasibility of graphene in a wide variety of markets. And what we have observed over the last several years is we know that customers are doing their application testing programs. So they're testing graphene in a given application to see about repeatability and about feasibility from a technical point of view. And the next step would be commercial adoption. So that's why you may have seen a post from us earlier this year. We really feel that this year, 2026, is the year of commercial adoption. And that is based on our knowledge and observation of what customers are doing with graphene behind the scenes and how far they're getting with their application development. So at this stage, we know this material works. We have commercial producers that have increased the scale of production, and we have competitive price environment for that material. So the next stage is finish the application testing and then roll out into production. A key component of this has also been regulatory approval. And we've seen consistent progress on the regulatory side with the approval of graphene in Europe under the REACH consortia and in the United States through EPA consent letters and approvals for the use of graphene in the US. That has also made progress. We've had several companies, including an announcement that's come out today about one of our member companies that has achieved EPA approval status. And so these are all signs pointing a green light towards commercial adoption of the material.
There are, I think, a couple of questions about the standard. That's the graphene classification framework. So the first one, I think, is about does the standard specify which techniques or methods can be used to classify the subcategories of graphene? So yeah, there are about 19 properties that are defined in the standard, which can be used to completely determine the performance or the characteristics of graphene. These are also referenced with the testing method that can be used for them. So for example, if you're looking at sp2 bonding or defects, then Raman spectroscopy can be a very good tool for that. So the standard defines what testing method can be used for defining all these properties. The second question is about the graphene classification and how would you classify CVD graphene and standardize the spec sheet. So the graphene classification framework also, CVD graphene can be defined more on the monolayer graphene side. You would have, if it's a single layer of graphene. And the GCF has a standardized format for defining how a TDS of a CVD graphene should look like. So if your material is CVD graphene, monolayer graphene, you can refer to the standard. You can see how the TDS can be made and what properties should be reported.
Absolutely. One of the other questions we have, and I think we're going to have to draw to a close as we come to the top of the hour here. So I'll take one more, and maybe you take one here, or maybe I'll jump in at a last minute on another one. But one of the questions is about the form factor. Is it always in powder form? And Chirag, you just answered the question about CVD graphene, which is typically on a substrate as a pure crystal. Graphene can be in a dry powder. That's typically how it's processed. It can also be in a paste. It can also be in a suspension of liquid. It could be water. It could be another carrier. And it can also be master batched into pellets. So for example, in polyurethane or polypropylene pellets, nylon, basically any of the plastics, graphene can be incorporated into. And a common way of preparing this is put it into a master batch so that the customer doesn't receive a black nano powder. They receive a master batch formulation that they can drop in. So that's important to know. But these are the kind of things we can advise you on. If you do have questions, do not hesitate to reach out to us. That's what we're here for, is to help you guys answer these questions. Do you
Yeah,
want
one
to
of
grab the
the
last one, or I've got another one if you want to.
I have a very short one, which was, I think, asked by a few people that will we get the slides and is the is the presentation recorded? So yes, after the webinar, as Terence mentioned, within the next 24 hours, the recording and the slides will be sent out to everyone who has registered. So yeah,
Excellent.
I'll leave the last one to you.
Excellent. Well, one of the questions was about scaling, like, for commercial adoption, can we scale? Um, I have absolutely zero concerns about the ability of this industry to scale to meet the demand for these materials. There are very reproducible production processes. There are very scalable processes. And for investors that are looking at the sector, the CapEx to stand up a graphene production facility is extremely low compared to many other industrial processes. And so the scalability and the repeatability, and also some of the production processes lend themselves to high scale production. That's not my concern. I think the biggest concern in the market today is educating customers to not be put off when they see, this is a material at $350 a kilo, and I'm using a polymer that's at $15 a kilo. How in the hell can I use graphene? Well, it's because you're using tenths or hundredths of a percent to get an engineered outcome from it. And that's the thing that a lot of people just do not understand. And the second is the fact that graphene is a family of materials, so it comes in many different flavors, and that can be confusing. And I can understand that. So, rather than struggle with that, you should contact somebody like ourselves where we can help you navigate that and give you independent, unbiased information, science-based information to answer your questions so that you can then pursue that and see whether or not graphene can solve your problem. Graphene, believe it or not, doesn't solve every single engineering problem in the world, although it's astounding what it can do. But we'll give you that answer too. If it's not appropriate, we will certainly tell you. We're not here to push graphene. We're here to help educate people on whether or not this material is a good candidate. With that, I want to say a huge thank you to my colleague, Dr. Chirag Rawani. He's an incredibly important part of our team. He's based in Manchester, UK. I'm based in the United States. We have colleagues distributed where we can help you wherever you are in the world. We have members from Australia to South America, the Middle East, to North America, etc. So we're here to serve you wherever you might be and whatever challenge you might face. If we can help you with your advanced or engineered carbons, please reach out to us. And with that, Chirag, do you have any last words you want to say to our audience before we conclude?
Thank you for attending the webinar, and thank you for sitting right till the end. Many interesting questions. We could not fit all of them, but please reach out to us if there's anything we can help you with. If you're unsure about your materials, you're not sure what's the best application for it, where does it fit, just reach out to us. Thank you.
Excellent. Thank you all very much. Have a great rest of your day. We appreciate you being here. Thank you.